Hello, hello. I'd say it's close enough for me to get started on here. If there's anyone watching, greetings, greetings. Welcome to the live stream. Today we're going to be doing some maze generation in processing. And if you don't know what processing is, it's a Java library. I guess a library is the best word for it. But it's really, really good to do visualizations and things of that nature. So here, let me get you onto my screen. And that should be good. Yeah, it looks like we're all good. So, what do we mean by maze generation? So let me go ahead and try to explain what I mean by this. So when you think of a maze, typically you think of like a top-down representation of like boxes and various things. So let me go ahead and make a line over here so I can show you. So maze gen. So when we have this idea of maze gen, typically what we're gonna do is we're gonna have this field of bunch of squares, like a grid. And there's a couple of different ways that we can show this idea. And that's to have either a grid of boxes where the paths are defined by which, like, by boxes being colored in or boxes being empty. So for here, for example, we have a path that's represented by boxes being colored in and not. So the path would be going this way and then going down through there. Or the other idea of a maze, which is probably more common if you're working with like graph paper, for example, is, oh, that was a terrible line. If you're working with graph paper, is to have the maze be represented just by walls. So you have this kind of idea of a maze. Rather than filling in boxes, you just have the raw walls. And both are easy enough to do in code. I think that for this particular example, we're gonna go with the idea of having walls because I think it's not necessarily more interesting, but it's the one that is better, more easier to like understand and code. Because the way that this algorithm works is you have some sort of starting square, right? Let me give my space a little bit more room. So you have some sort of starting square, right? And the algorithm, it chooses one of its neighbors and it selects one of them. So since this is going to be on the corner, say it selects this box right here, then it goes ahead and continues the path towards that box. And it does the same thing again. It chooses one of these two. Say it chooses this one. Okay, that's all good. And then it keeps going. Maybe it chooses this one. And then maybe it chooses this square here. And all the while, it's deleting these walls in between each square. And then maybe it has a choice between these two. And if it chooses this square, right, suddenly we have a path that no longer has any squares next to it to advance. So it goes backwards to the next square that has an available neighbor, and then it chooses that as the next continuing path. And it keeps doing this all the way across the maze until it has a completed maze. This is known, I believe, as Dijkstra's algorithm. I think that's what it's called, Dijkstra's algorithm. But let's go ahead and jump into processing and write some code. All right, so first thing you do with any processing sketch, you're gonna have a setup and a draw function. Perfect. I know it's a bit of an argument whether you have your braces on the same line as the previous line or on separate lines. I do it on separate lines just by like preference, and that's how I've always done things. So why shake up the meta? We're just gonna have a canvas size of let's just say 650 by 650. And then we're gonna have just a blank background for now. Just so we know that everything is working in tip-top shape. And yeah, we do get a background that's just gray. So that's good. Then, okay. Now, when we have this idea of a maze and it's going through these little boxes, what I mean by the little boxes is we're going to have this idea of, yeah, these little boxes. I'm going to call them cells. And these cells are going to be inside of the grid. So we're going to say class cell. And then it's going to have a constructor function. Okay. And then now, in order to make this grid of cells, we're going to have it be in an array. So it's going to be an array of cells, and it's going to be a 2D array, so it's going to have both of those brackets. And we're just going to call it grid. And then in addition to this grid, we are also going to need a size of each cell. So we can store that as an integer and call it cell size. I like to camel case things. And for now, let's go ahead and set it to something kind of big, maybe 50 to start out with. Yeah, I think that seems fine. And then now we need to go ahead and represent this grid and show it on the screen. So in our cells, when we're going to activate the cells, we're going to have it get a set of coordinates. So we're going to represent that as an X and a Y. And then when we create the cell, we want to tell the cell what those X and Y are. So when we create the cell, it's going to give us an X and a Y. And then we can set our personal X and Y to those. Beautiful. Now we're gonna have to create a function to actually show the cells. And we're gonna do void show. And all it's gonna do right now is just draw a rectangle at whatever X, Y coordinate it is at. And since X and Y, they're not actually coordinates on the screen, but rather indexes in an array, we're going to multiply those indexes by the cell size to get the position on the screen that they should be. And then Y times cell size. And then the actual size of each cell is the cell size. Perfect. And then it's going to have no fill, but it's going to be a stroke of 0 with a little bit of stroke weight as well. Say 5. So now we have a function that shows our cells, but we don't actually yet have any way of showing our cells in the code that we run, because first we need to initialize the grid and then initialize the cells that go inside of the grid as well. So now that we have the size, we're going to go ahead and use a couple of for loops to initialize the grid and all the cells that go inside of it. So our grid is going to be equal to a new cell array you do it like this, with the first size being the width divided by our cell size. And then the second one will be the height divided by the same cell size. And that should all be good because both the width and the cell size are integers, so it's going to give us an integer result, so we don't have to worry about flooring that or anything. And then now that we have this grid to work with, we're going to write a nested for loop to insert our cells into that grid. So integer I, for integer I, which goes from 0 to our grid length. We're going to have a second for loop inside of that. Call it J. And that's going to go from 0 to grid at I dot length. And the reason we say grid at I dot length, is that we have the I variable first, and then the J variable is second, because I is going to represent our X coordinate, and then J is going to represent our height coordinate. And then now we have to say grid at I at J, because it's a 2D array, so it's an array of arrays. We're going to say that is equal to a new cell passing in that I and J. So now we have this concept of a grid, and we also have the grid populated by a bunch of cells. Now in our draw function, we actually have to, show that we have these cells. So we can go ahead and copy the same for loop, but instead of creating a new cell, we can say, okay, grid at ij, go ahead and show yourself. And this should be all good. So let's run it. And you can see that we now have this grid of lines, and each cell is the square of each each cell has these 4 lines around it, the box, and so now we have this grid in our system that is representing our cells. Awesome. Okay, so now let me go back to here. So now that we have this grid on our screen, now we have to say, okay, so each cell right now is represented by a box, right? Just a rectangle. We want to try to separate the idea of the rectangle and the cell, because when we're erasing walls, we can't erase a rectangle. So instead, we're going to represent the rectangle as 4 distinct lines, and the lines are going to be connecting, but this is just so I can show you what I mean. So we're going to represent the rectangle as 4 lines, 1 line being each wall of the cell, rather than having the rectangle be what is represented. So ditch the idea of a rectangle. We're going for 4 lines to represent our cell. Okay, so let's jump back into processing. And in our cell class, we want to have a representation of our walls. So the best way to do this is with a Boolean array of size 4. Because each cell has 4 walls that can either be on or they can be off. So that's why it's a Boolean value. And this is giving me an error. Consider variable declaration. Oh, we have to give it a name. Call it walls. And then for now, we're just gonna have the walls be totally random on or off before we actually do any fancy calculations. So we're gonna say for int I is equal to 0 to walls.length. So this should go through each of our walls. And then now we can set that wall value to either true or false. And we can do so in a fancy way to make it randomized. So walls at I, that's going to be equal to random of 1 is less than 0.5. Because random of 1 gives us a value from 0 to 1. And then, this is complaining, it's walls. Random of 1 gives us a value from 0 to 1. And if that value is less than 0.5, it's going to put a true. If it's greater than 0.5, it's going to put a false. And that's an easy way of having a random Boolean value. So now, instead, in our show function, instead of having a rectangle, we wanted to have this idea of 4 separate lines that make up the rectangle. So we can go ahead and get rid of this. So we can get rid of the rectangle, and then we're gonna have this this line. And we can do this in a couple of different ways. But I'm just gonna do it in 4 if statements. So if walls at 0, that means our first wall is true. Then we're gonna go ahead and draw the line on the top. And let me go ahead and put that into Leonardo. So our walls, they're gonna have indexes of 0, 1, 2, and 3, because there's 4 of them, and arrays start at 0. And we're doing it clockwise because why not? We can change it however we want to. We just have to make sure that whatever one we do choose, we continue using that one. So 0, 1, 2, 3. So if walls at 0, we're going to be doing the top side of the cell, which just so happens to have this exact position first of it. So we're going to take that position. And we're going to say, okay, draw a line starting at the X and Y. And it's going to go to the same X and same Y. But since it's the top, the X coordinate changes, the Y coordinate does not. So it's going to be X times cell size plus cell size. Just like this. And then we make sure to close off our line. And then we should be good. So we can go ahead and show this now. And we'll only see horizontal lines. Because we're only going to be drawing the top side of the cells. And this actually is a pretty neat way of like drawing randomized newspaper lines. If you've ever seen like the artistic renderation of like newspaper articles when they're not really like wanting to talk about anything and they just want to have like an idea of a newspaper, this is a great way of doing it. Just have random horizontal lines that are parallel. Run that a couple more times so you can see the difference and that it is indeed random. So now that we have walls at 0, we can do the same thing for 1, 2, and 3. But we have walls 1, or 0, 1, 2, and 3. So walls at 1, if we come back here, walls at 1 is going to be the right-hand side of the cell. So it's going to have the position of the X plus cell size, Y, and it's going to go to X plus cell size, Y plus cell size. So that's this line here. So let's go ahead and do that. So it's going to go from X plus cell size to Y. That's okay, that's good. And then it's going to go to Y times cell size plus cell size. Beautiful. And then the walls at 2 is going to be the bottom, which starts at X plus cell size, Y, or X times cell size, Y times cell size plus cell size. Because it's the bottom. And then it's going to go 2X times cell size plus cell size to Y times cell size plus cell size. Beautiful. And then the walls at 3 starts in the upper left corner, and instead of the X coordinate being the one that changes, it's the Y coordinate. Now if we run it, we should see a bunch of random walls, and we're starting to get closer to the idea of a maze. You can see even some paths being formed here, but these aren't like actual mazes yet. These are just a representation of our walls, and to show you that indeed, yes, we do have walls. And this does look like more walls than 50%. And that's because our cells share walls together. Like the left-hand side of one cell is the right-hand side of another. So we need to have those correlate together if we wanted to actually show 50% of the walls. But we'll do that in a second once we actually get the maze generation going. Okay, so now to recap. We have this idea of a grid, and each cell is represented by 4 separate walls, and we have that all set out now. So now we actually have to program the algorithm that generates the maze. Give me 1 second. This music's a bit loud. Okay. So now we actually have to show the algorithm that goes and generates the maze. And the way that we do that is we're going to have, in our grids, we're going to have the starting cell. It's usually chosen arbitrarily. We're going to represent it with the cell in the upper left corner. So this is B00, 0, and it's S for start. And the way that the algorithm goes is, okay, check each 4 of its neighbors, and then choose a valid neighbor to go to next that has not been visited yet. So this neighbor is invalid because there's no neighbor there. So we want to choose one of these 2 neighbors to be next. So if we go into our processing and into our draw function, because we're going to do this because we want to show the generation. So we want to show each cell being chosen one after another. So we're going to need to have a couple of things here. We're going to have a cell array that's called... Actually, no, because we can represent visited in our actual cell here. So we're going to have a Boolean value called visited, which is set to false by default. We're going to have a clean slate. No cells are being visited yet. And then we're also going to have here all of the walls being on, because we're no longer wanting to test that we do have 4 separate walls. We just want them all to be on and good. So now that we have an idea of cells being visited or not, now we need to have a current cell, because we're working 1 cell at a time. And then when we choose a neighbor to go to, we want that one to be the new current cell. So an idea of a current cell. And we're also going to need an idea of a stack, which is a computer science term that just is a list of data where you input data on one side, and then when you want to grab data out of it, you go from the same side of it, like you're stacking dominoes. Or not stacking dominoes, but like you have if you ever played with those toys, before, where you've got like a central pillar. I'm drawing all diagonally. You've got a central pillar and you've got these like rings, and you like put them in a stack. You can put them in the stack one at a time, going from the top down, but when you take them off, you have to take off the top before you can take off the bottom. So that's the idea of a computer science stack. And we represent that with just an array, but we're gonna use an array list for this example here, because it's the one that I'm most comfortable with, and I think because it has a size that you can alter rather than an array which has a distinct size. So it's nicer that way. So we have an array list of cells, and we're gonna call it our stack. Okay, perfect. So I'm gonna skip this song because it's super mind flooding. Okay, so we've got an array list of cells that we're calling our stack. And the algorithm, so first before we start the algorithm, we need to have a current cell, and we're gonna represent that current first cell as the upper left-hand corner, which is our 0, 0 in our grid. So current is going to be equal to grid at 0, 0. Beautiful. And then in our draw function, we can actually have the algorithm. Okay. And let me, and we're going to search for maze generation. Okay, so the one that we're doing is the DepthFirst search algorithm using the recursive backtracker. So let me copy this idea here. Let's see. Invoked. Yeah, recursive. So start with a current cell, and that's going to be our upper left-hand cell. Mark the current cell as visited. So we can do that in our code like such. So we can say current dot visited. Current dot visited is equal to true. Beautiful. All right. And then while the current cell has any unvisited neighbors, choose one of the unvisited neighbors, remove the wall between the current cell and the chosen cell, and invoke the routine recursively for a chosen cell. And then this one says implemented with an illicit stack. So this is the one that we're going to use rather than a recursive definition. We're going to be using the idea of a stack. So choose an initial cell, push it to the stack. While the stack is not empty, pop a cell from the stack and make it the current cell. If the current cell has any neighbors which have not been visited, push the current cell to the stack, choose one of the unvisited neighbors, remove the wall between the current cell and the chosen cell, and mark the current cell as visited and push it to the stack. Okay, so we've got an initial cell. We've marketed it as visited. Next, we need to push it to the stack. Okay, so we've got a current cell, marketed it as visited, and then we push it to our stack. Stack.push current. Nice and easy. And it's not push, it's actually an add. Nice. And then the algorithm says, while there's no while the stack is not empty, we're just going to say use an if statement because we're going to be using the draw as our loop rather than having a while loop. So if stack is not empty, so if stack.empty, how do I spell empty? There we go. So while our stack dot empty is equal to false, but it's not stack.empty because that doesn't actually exist, but we can use size. And while our stack size does not equal 0, there we go. So while the stack size does not equal 0, we're going to take a cell off of the grid and mark it as our current cell. So rather than having current be equal to here and here, because we are going to have a the current be in our loop here, then we don't necessarily need to have current already set. But I guess it doesn't really matter. So we're going to go ahead and pop the stack off and set it to our current cell. I believe, yeah, pop a cell off the stack and make it a current cell. And then if the current cell has any neighbors which have not been visited, do the rest of the things. So the way that we're going to be popping off the stack is we're going to set our current cell equal to the stack.get stack.size -1. So this will grab the most recently put cell in our stack. And then because it's not an actual stack, we have to remove the cell that we just got out. So stack.remove. And it's going to be the same cell. Like that. Perfect. So now we've got a current cell, which is the most recent cell to be put onto the stack. And then, if the current cell has any neighbors which have not been visited, push the current cell onto the stack, choose one of the unvisited neighbors, remove the wall between the current cell and the chosen cell, mark the chosen cell as visited, and push it to the stack. So, now we have to get this idea of neighbors, because we have this idea of a grid, but we have no idea what a neighbor is, let alone how to represent that in code. So if we pop over to Leonardo here, so now we have this idea of a cell, right? And it has an X coordinate and a Y coordinate. And its four neighbors are this one, this one, this one, and this one. This neighbor has the same X coordinate, but the Y coordinate is minus by 1, right? Let me fix that line there. Perfect. This cell has the X coordinate increased, but the Y coordinate is staying the same. This one, same X coordinate, but the Y coordinate is increased by 1. And this cell has the X coordinate subtracted by 1, but has the same Y coordinate. So now we have this idea of how to get those neighbors. So in the algorithm, it says while the cell has no current unvisited neighbors. So let's go ahead and create a function for that. We're going to be calling it, it's going to return a Boolean value, true if it has any unvisited neighbors, and false if all of its neighbors are have been gone away. So we're going to call it neighbor check. And yeah, we're gonna call it neighbor check. And the algorithm, if the current cell has any neighbors which have not been visited, we're gonna push the cell that's currently up onto the stack and choose one of its unvisited neighbors. Okay, so we're gonna also need a choose neighbor function, which is gonna return a cell for us. Okay, so we've got a neighbor check, which sees if it has any unvisited neighbors, and then a function to choose one of its unvisited neighbors once we've checked it that it actually has any. So we're going to get rid of the error lines by just having it return false and null, respectively. Okay, so the neighbor check, we can short circuit it in a way such that it doesn't have to check every neighbor. It's going to check the neighbors, the top, then the right, bottom, and left. And then if it comes across a neighbor that exists and also has not been visited, then we can end the function right there and just say, yes, true, we do have a neighbor that has not been visited yet. So let's go ahead and write that. So if our x is greater than 0 and grid at x minus 1, but keeping our same y, dot visited unreachable code. Oh, because this is there? Okay, so if our x value, so our current cell's x value is greater than 0, so meaning it's not, like, it's not at 0 and it's not below 0, which doesn't make any sense. So we're only going to be using this code if we're not in the top right, or the upper portion. No, the left portion of our screen. So if our x is greater than 0 and grid at x minus 1, comma y, dot visited is true, but we want that to see if it's not visited. So check it if the visited is false, then we're done. We can return true. And then we want to do the same thing for each of the other 4 neighbors, or other 3 neighbors. So if our y is greater than 0 and grid at x, y minus 1, if that has not been visited, then we can go ahead and return true as well. And then if our x is less than our grid length minus 1, then we can go ahead and check at grid plus 1 y. And then the same goes for the y as well. And the reason I'm saying grid at 0 is just I need to have a way of representing that second array, and it's just the base case, the one that's always going to be there regardless. And then if none of these trigger, then we know that we don't have a neighbor that is available to us, so we return false. Nice. So now we've got this idea of a neighbor check. So let's go ahead and use it down here. So if our current neighbor, or not current neighbor, but if our current cell dot neighbor check, so if our cell has a current neighbor, then we can do stuff. If it doesn't, no worries, we don't have to do anything else. But if our cell does have a neighbor, we want to push our current cell onto the stack. So stack.add current. And then we want to choose a temporary cell, or we want to choose another cell and from the current list of available neighbors. So we're just going to say cell temp is equal to current dot get neighbor. Like so. And I don't believe I called it that. It's choose neighbor. Ah ha ha. There we go. So now we have a cell temporary that comes from our current neighbors. So choose one of the unvisited neighbors. And then now we need to remove the wall between the current cell and the chosen cell and mark the chosen cell as visited and push it onto the stack. Okay, so we're gonna get to that in just a second. First, we're gonna have we're gonna implement the choose a neighbor code. So if we go back to our cell, and we're gonna say, okay, choose neighbor. We're gonna have a list of neighbors that are good, and then we're gonna choose a random one of those neighbors, if that makes sense. Okay, so we can actually use some of the code from the neighbor check to make our life a little bit easier. So we're gonna have an array list of cells. And we're gonna call it our neighbors. Perfect, and we're gonna go ahead and initialize it. Nice. And then in our neighbor check, because we're gonna check our neighbors, we're always gonna check our neighbors before we grab a neighbor to choose from. Then we can go ahead and say, okay, so if grid at x minus 1 y visit is equal to false, we can add it to our list of current neighbors. So neighbors.add, and it's going to go ahead and grab this particular cell. Just like that. And then since we want to check the remainder of the cells, we're not going to return true here. We're going to continue onward into the code. And then we're going to go ahead and copy this and paste it in each of these. But this one is at x, comma, y minus 1. And then this one is at x plus 1. And the final one is at y plus 1. Nice. And then before we return false, we're going to have a condition that checks to see if we have any neighbors in our neighbor array. So if neighbors.size is greater than 0, that means we've got a neighbor in there. We can go ahead and return true. Nice. So that's that code all finished. And for our choose neighbor, we already have an array of current neighbors that we can go ahead and choose from. So we can say return neighbors dot get random or floor random neighbors dot size. So all that this code does is it chooses a random neighbor from the neighbors array that we initialized up in the code neighbor check. Perfect. So now we've got this idea of a temporary cell that comes from our current list of neighbors. The last step is now to remove the walls in between the current cell and the temporary cell. So the way that we do that is we're going to have a couple of if statements here. So if current dot x is equal to our temporary dot x, so if they're on the same column vertically, then we can go ahead and remove or check to see if it's has a greater than or less than of a y, because one of those needs to be different. So if our current y is less than the temporary y, so if our y is less than the temporary y, we want to remove this wall here. So this would be the 0, 1 second wall of our current cell and the 0th wall of our next cell. So remove the wall, the second, or the wall in index 2 of our current, and then our temporary, it's going to be an index 0. Nice. However, if our current cell is greater than the temporaries, then we just want to reverse it. Like so. So if the current x is equal to that, then we do this one. However, if they are not equal, then we need to figure out which one is greater. So if current dot x is less than temporary dot x, okay. If the current x is less than the temporary, so if our current x is less than our temporary, you want to remove the current's index 1 wall and the temporary's index 3 wall. So our current at 1, temporary at 3. Otherwise, remove the current's 3 and the temporary's 1. And then the final step, after we've removed the walls, is we need to add the temporary cell to our stack. And I believe that is all. Mark the chosen cell as visited and then push it to the stack. So we need to make it visited and then we can do that. So temp.visited is equal to true. And that's the whole algorithm, I believe. So if we run this, it should work all smoothly, provided that I've written everything correctly. Okay, perfect. So this is a great example. So what it did is it started in the upper left corner, made its way right and then down, and it followed this pathway, and then it got to here. And it got to here, and it no longer has any available neighbors. So what we need to do now is if the current cell has no neighbors, we need to pop off the stack until we get to a cell that has neighbors available to us. And I believe current.stack.get, we add the current one to the cell, we choose a neighbor. If it has any neighbors, right. So what did we do wrong here? Make this a little bit bigger here. Okay, choose initial cell, mark it as visited, push it to the stack. We did that up at the very top here. Mark it as visited, push it to the stack. While the stack is not empty, so if stack.size is not 0, then we pop a cell from the stack. We remove it. And then if the current cell has any neighbors which have not been visited, push the current cell to the stack, choose one of its neighbors, remove the walls between the current cell and the chosen cell, mark the chosen cell as visited, and push it to the stack. That seems like everything. Let's run it again. So yeah, once it gets into a corner, it seems to not be able to get back out. One more time for good measure. So yeah, it gets blocked itself into a corner and then no longer can get out. So I believe the way that we fix that is at the bottom here. We show all of them. If stack.size is greater than equal to 0 or not equal to 0, push the current cell. Add this cell as well. Stack.get stack.size -1, and then we remove it as well. Let me do some testing here. So we're gonna have, in addition to show, we're gonna have another function called void cur. Which is just going to have a rectangle wherever the cell is. With no stroke. Going to be at x times cell size, y times cell size, and then its size is going to be cell size. And then this is just so that we can see the current cell. We're going to call it current.cur. So now that we can see... Oh, okay, so now we know what's going on. So it goes along perfectly, and it does pop off of the stack, but then it immediately goes back. And it goes like back and forth, rather than continuing to go back until we've got a neighbor that's not been visited yet. And that's because when we check our neighbors, before we add anything to them, we want to make sure that the neighbors array is all cleared. And I believe it's just clear. Because what we were doing is we weren't actually updating the array. We were just adding additional ones. And whoa, it's going so fast you don't even know that it's working. But it is indeed working. So, look at that. We generated a maze. It went along the grid, and when it backed itself into a corner, it went backwards until it got to a cell that had a current neighbor, and then it carried on its merry way. And look at that. We have done it. So let's go ahead and play around with this a little bit. We can decrease the cell size to have a bigger grid. And let me go ahead and make the background more visible or brighter, just so we have more contrast. And now you can see our little red dot is going around and it's carving its way through a maze. And then when it gets into a corner, it goes back through the maze and continues onward. And that's it. That is the recursive backtracker algorithm for generating mazes. If there's anyone watching this, I appreciate you guys watching. I hope you all had a great time. And I will be making this code available on GitHub for you guys to look at later sometime tonight if you want to play around with it. And I bid thee a good day.